for inviting me. Okay, so today I'm going to give this talk on the low phase rank approximation problem. My name is Di Zhao from HKUST, and this is a joint work with Seizhen Kong, who actually recommended me to this talk, and he got his PhD from Melbourne University. So yeah, you must be familiar with him. And this is also joint work with Axel Ring, who is another postdoc in our group, and Li Qiu is our boss. So let's get started. Sorry. I will, in this talk, I just briefly, I will first start with the definition of phase. So this is a low phase rank approximation. So we need to make sure that we understand the concept of matrix phase correctly. And then I will formulate the problem and try to characterize the solutions to the problem. And in the end, we conclude this talk. So what is the matrix phase? So we start with a scalar. So we consider a non-zero complex number, C. It usually can be written in the polar form, that is C equals to its magnitude times e to the power of j angle of C. So since it's non-zero, then its magnitude is greater than 0, and its phase is just in a 2 pi interval. Okay, so for this scalar, we can define its gain and phase very quickly. But what about a matrix? The magnitudes or gains of a matrix are usually defined in terms of its singular values, and this is like widely accepted. So for a square matrix, which is n by n, then we have n singular values, which are the gains of this matrix. But what are its phases? So this is a bit controversial because in many years, people don't have a universal agreement on what is the definition of the phase of a matrix. Let's see what we want, like what is desired properties of a phase that maybe maybe workable as a alternative definition. So the phase of a matrix should definitely cover the scalar case as a special example. And we also hope that the phase is comparable to the gains, in the sense that for an n by n matrix, it should have n phases, like we know that it has n gains, so that we can compare the phase and gain. And in the end, and the most important thing is that the phase should be easy to compute and suitable for analysis. Here, the analysis depends on the application. And we will see that if it is in the area of systems and control, and when we formulate the feedback stability stuff, then this phase is good. Okay, so after all, we will use the definition of matrix phase that is rooted from the works of Charles Johnson from 70s to 2000. And this phase is only defined for the sectorial matrices. And let's see what is the definition. Okay, so let's first recall that the phase of the number 0 is undefined because it doesn't contain any phase information. So this gives us a hint that not all matrices possess phase information. And this is the reason why we only define phase for sectorial matrices, because here the set of sectorial matrices, it's good for us to introduce a clear definition. And a matrix is said to be sectorial if its numerical range doesn't contain 0. And the numerical range is just, we can see that here this numerical range of C is just the quadratic form on C. Here we have x star Cx, and this x is a complex vector with unit length. So this numerical range is a convex closed object on the complex plane. And we see here on the plane, we have this gray part is just the numerical range. And with this convex object, we can actually, before we introduce the definition of phase, we can actually go a step further to to see what are sectorial matrices really, I mean, make some connections to what we already know from the sectorial matrices to those. And if we use this notation, so we say that this matrix is sectorial in the interval alpha beta if the angle of the element in this numerical range is in between this alpha and beta. Yeah, we denote the set of matrices in this way. And if this interval is chosen to be this minus pi over 2 to pi over 2, then the matrix is nothing but a strictly positive real matrix. And in other words, the real part of all its eigenvalues are strictly positive. So similarly, if we choose the interval to be minus pi to 0, then this matrix C is just the strictly negative imaginary matrices, which means that the imaginary part of all its eigenvalues are strictly negative. So these two concepts are actually well established in control theory, because we know that if we take one step further, then we are working, if we are consider a linear time invariant system with its transfer matrix, and if that transfer matrix is strictly positive real or negative imaginary on all frequencies, then we simply call the system to be positive real system or negative imaginary system. And this kind of systems have been widely used in like formulating control problems, like in the mechanical systems and the passivity theory and all this stuff. So we see that these sectorial matrices are not completely new stuff. It's just do a little bit generalization of those well understood notions on the passivity, positive real, negative imaginaries. So okay, so with this set of sectorial matrices, we are ready to define the phase. So what are the phase? So a sectorial matrix is matrix C admits a sectorial decomposition. So here we write this C into this decomposition. And this T is non-singular, and this D is important because it contains all the information. Yeah, this D is unitary and diagonal. And this D is actually unique up to a permutation, which means that we can use this D as our definition for phase in the following sense, that we simply denote the phase of matrix C to be the phases of the diagonal elements of D. Yeah, just in this way. And we do a simple organization. We make phi 1 to be the largest, phi n to be the smallest. So okay, now we have n phases defined for the matrix just by this simple decomposition for sectorial matrices. Yeah, so we got n phases. That is what we hope, because we hope to compare with the gains. We know the gains are the singular values, and it has n singular values for a matrix. And now we have n phases for a matrix. So yeah, so far so good. Okay, let's do a little bit more comparison between the gain and the phase. So let's recall the singular values of a matrix C can be computed very frequently in these two ways. There are definitely many other ways, but these two are the most frequently seen. And the first is just by max minimum or minimax optimization over this objective function Cx. So this is like the most it's just common stuff. And we can also use the eigenvalue of the CC star, which means that we do this CC star and we take the ith eigenvalue and we take square root, we get the singular value. Okay, so these are the well-known stuff. And luckily, and which is actually very nicely, that we also has this kind of computation for phase. So we can do the max minimum for the phase, just replace the objective function from this gain stuff to this angle stuff. We take angle of this projective form, we do the max minimum, we get the phase. And we can also use this CC star stuff, but instead of using CC star, we use this C minus star. Here, this star is just the complex conjugate. So we take the inverse of C, then take complex conjugate, then multiply it by C. We still work on its eigenvalues. We work on the eigenvalues and we take the angle and we take half, like this, take square root. Okay, so this is like very parallel stuff. We see that the canonical faces are actually comparable with the gains in many sense because they can compute in a similar way. They already defined in a similar way. They can also be computed in a similar way. So they must share many common properties. That is very attractive. And the first conclusion is that the computational complexity of these two stuff are actually more or less the same, because we see that here we only do multiplication and we do eigenvalue decomposition. So, okay, so this is all about the like preliminary stuff on matrix phase. And there have been some applications of the matrix phase, mainly in the area of systems and control. And we use the phase to analyze the feedback stability of linear time invariant systems and networks via the so-called small phase theorem, like the small gain theorem we have for many years. And we got some conference papers published. And we also try to extend the concept of phase of matrices to the phase of nonlinear operators, also known as those nonlinear systems and their feedback interconnections via the so-called nonlinear small phase theorem. So we know that and we also got a paper published, and yeah. So here today I don't focus on this kind of this line of research, because what we are really concerned is that we hope to compare more about the phase and the gains in terms of more like discrete type research. Like we try to formulate the phase rank stuff, and we try to compare with those rank that is defined by the singular values. Okay, so this is the target in this talk. We try to formulate this low phase rank approximation problem. Yeah, let's just jump into the definition of phase rank. So this is a very simple definition, because we know that the rank is just the number of the non-zero singular values of a matrix. Then the phase rank is naturally defined as the number of its non-zero canonical phases. So we know that a matrix have n phases, then the number of its non-zero phases are just the phase rank, or we simply call it Planck, which is like the rank and the Planck. Yeah, it sounds similarly and good. So let's see simple example. That here we have this rank 1 matrix and Planck 1 matrix. So this rank 1 matrix can usually be written as a column plus a row, or all in this singular value decomposition form. And we put the singular values in the diagonal. We see that here the first one is non-zero and the remaining two are 0. So it's a rank 1 matrix. And what is a Planck 1 matrix? It's very similar. So we use this so-called sectorial decomposition. Here is T star and T are non-singular. And we put, those diagonal terms are important. And the first phase of this matrix, pi over 4, is put in this way. So this is just a number with unit length, and its phase is pi over 4. And the remaining two diagonal terms are just 1, which means they don't have phase. Sorry, their phase are 0. So this satisfies the definition of Planck 1 because they only have one non-zero phase. Yeah, so very simple. We just give another definition. So this is then let's do a little bit more comparison, because we know that low rank matrix are good and will like accepted as an important tool. So let's try to understand more about the low phase rank matrix. So yeah, let's look at the most extreme case. So if a matrix has 0 rank, then it's just a 0 matrix. But if a matrix has a 0 rank or 0 phase rank, then it is actually a positive definite matrix. So this is quite different. You see that a 0 rank matrix is 0, but a 0 phase rank matrix is positive definite. And if a matrix has a low rank, then it must be singular. And in the end, I mean, on the other hand, it should be very easy to, has some advantage in storage, because we know that a low rank matrix, even if its own dimension is very huge, it can be stored like with a small space. So this is good. And if we have a low phase rank matrix, we know that by definition that it should be non-singular, but it should be somewhat close to the positive definite matrix. So this kind of parallel gives us some intuition that we may take advantage of the low rank concept similarly as the low rank concept. And in the area of systems and control, the most frequently used low rank approximation is just for this so-called model reduction. We use a simple mathematical model for a complex system. So this is what we usually mean if we hope to do low rank approximation in systems and control. So we hope that this low phase rank approximation will also give us some low complexity description of a complex system, just like the rank, but in a different perspective, because we know that the gains and phase are naturally like different. So we expect that this low phase rank description will give us an alternative way to like simplify a complex system. Okay, so let's see what is a standard low rank approximation. After that, we will move to the formulation of a low phase rank approximation. So the low rank approximation is actually it can be complicated, but here we start with the standard form, which is very simple. So here we are given this matrix A with the object. This E is a low rank approximation to this matrix A, and we measure their approximation error in this way. So this sigma bar is just the largest singular value, or in other words, the spectral norm on this difference of matrix A and E. So A is the object, E is its low rank approximation. So that's it. And the solutions are given by the well-known Schmidt-Mirsky theorem, which says that this minimum is nothing but the R plus first singular value of this matrix A. Very nice solution. And the optimum is attained on E star, which is just a truncation of the singular value decomposition of matrix A. So how we truncate it, it's very simple. We only, we put all the diagonal, so here this S contains all the singular values, and we truncate off all the largest R terms, and we replace those terms with 0, and we keep the smaller part, and we obtain a truncation, and that truncation is just the solution to the by the Schmidt-Mirsky theorem to this problem. So so we got a closed form expression for this low rank approximation. Okay, so as a motivation, we may first formulate this so-called standard low phase rank approximation in this way. So we also have this matrix A as our object, but we assume it to be sectorial in the interval alpha beta. And this E is the approximant to this matrix A. And this E inverse, AE inverse is a approximation error term. Okay, so we see that we divide E, we use E to divide A from both sides actually. In this case, this E only contains half of the information of A in the, in the ideal case, if we allow this E to be full phase rank, then it can contains at most half of square root of this matrix A. So we call it a half approximant. And this term is this E inverse A E inverse term by taking this largest phase. And actually this measures the phase size difference of the phase size of the approximating error, or just the phase size difference between this matrix E and matrix A. So very similarly to the low rank approximation, we just define this low phase rank approximation. And we use this low phase rank E to approximate matrix A from both sides symmetrically. So very like, because why we do both sides? Because we know that in general, the multiplication of matrices can't be swept, like they don't commute, like they don't commute like the addition or subtraction. So we have to do this, and this is one reason. Another reason is that actually we can interpret the problem in another perspective, like the mean of matrices. So we know that the matrix can several means can be defined for matrices. The most simple one is the arithmetic mean, which is closely related to the low rank approximation problem. It's defined like this. So for matrix A and B, its arithmetic mean is just defined as the sum of A and B over 2. Okay, so we know that in the low rank approximation, we measure the error of A and B by using A minus B, and then we take norm. And A minus B is just A plus the opposite of B. So we got the intuition that the low rank approximation is related to the arithmetic mean. So what about a low phase rank approximation? So we know that the phase is actually more suitable to be operated in the sense of multiplication instead of addition or subtraction. So we don't use arithmetic mean anymore. We use the geometric mean, and very nice, very luckily, for sectorial matrices, the geometric mean are well defined. So the formal definition is given by this formula, but nevertheless, we know that we can see this equation. So for a matrix A and B, both are sectorial, its geometric mean G satisfies this equation, and this is all we need. So with this equation and with this definition, we can restate the low phase rank approximation problem in the following way. So given this A as our object, we try to solve this problem. So here B is no longer the approximant, but we can find the approximant by solving this B. And here we don't have those strange E inverse A E inverse stuff, but we have this geometric mean between this B inverse and A. So in other words, the low phase rank problem is actually formulated in terms of the geometric mean of matrices. And this is a nice parallel or counterpart to those low rank approximation, because they are formulated in terms of arithmetic mean. So we got another parallel, and this is good for us to understand the problem. Okay, another question that people usually raise is whether a low phase rank problem can be reduced to a low rank problem. So yeah, because we know that low rank problems have been worked on like for many years. The most direct way to study low rank approximation is by reformulating it into a low rank approximation. But in general, yeah, they do have some connections, but in general, they are not equivalent. So we actually, the phase rank of matrix A can be lower bounded by this rank minimum rank, yeah. So given matrix A which is sectorial, then the phase rank of A is greater than or equal to minimum rank A minus M, where M is just a positive definite matrix. Or further, it can be written in this way: another minimum rank problem. And the equality is actually can't be replaced by the inequality can't be replaced by equality because we have this counter example. So here we have this 2 by 2A whose rank is 2, and after subtracting this matrix M, then the determinant of A minus M is 0, which means that its rank is 1. Its rank is 1, and we have this strict inequality here. So so from this simple example, we see that the phase rank can be somehow approximate or lower bounded or upper bounded by the rank, but in general they are not equivalent. So a low phase rank problem is in general can't be like replaced or reformulated in terms of a low rank approximation. Yeah. So this is the difference between these two formulations. Okay, so now we try to characterize our solutions to the low phase rank approximation. First, let's recall the famous Schmidt-Mirsky theorem as we have been talking about that it solves the low rank approximation. So this is a low rank approximation, and its solution is given by the Schmidt-Mirsky theorem. So for the low phase rank, we develop a Schmidt-Mirsky's flavor result like this. So for the simplicity of expression, we restrict A to be positive imaginary, which means that it takes phase from 0 to pi. All its phases are non-negative and in this range. Okay, then the solution to the low phase rank approximation is given by this. So after the approximation, so the minimum of the approximation error is just the R plus first phase of matrix A. And the optimum is attained on each E star, which is a half R truncation of the sectorial decomposition, A equals to TD T star. So this half R truncation of sectorial decomposition is very similar as here, this R truncation of singular value decomposition. So half means that we first take square root of this matrix D. And R truncation means that we truncate off the R largest terms in the matrix D, and we replace those terms with 1 because 1 has 0 phase. So with this truncation, we get the solution to the low phase rank approximation problem. And let's see a very simple example. So this matrix A is given like this. So it's a complex matrix because here we see that we have this J as a purely complex number. And we know the canonical phases of matrix A is like this. It's 3 pi over 4 and pi over 4. It's all positive. Optimal Planck zero approximation is given by this identity because Planck zero means the approximant has to be positive definite. And the best positive definite approximation to this matrix A is just the identity matrix. Easy to understand because this matrix is unitary. And the optimal Planck 1 approximation is given by this. So these two, the left and the right terms are just, we can see it as like the sectorial decomposition, the T term in the sectorial decomposition. And the middle part contains all the information of this E. And we see that it is indeed a Planck 1 matrix because here the second term has 0 phase. And the first term contains the phase 3 pi over 8, which is half of 3 pi over 4. Because we have already mentioned that this is a half approximant, so it only contains half of the phase information to the matrix A. So this is how we do low phase rank approximation and what are the solutions. And we see that this solution is not very nice because we may hope that it should contain all the phase information rather than half of the information. So if we want to like get a better way to characterize the solution, we may need to reformulate or formulate the low phase rank approximation in an alternative way like this. Okay, so first of all, let's admit a fact that the set of all sectorial matrices in this interval forms a smooth manifold with a certain metric that is defined on this set. So with this manifold, we can define the geodesic distance between two terms or two elements in this set. So a pair of elements in this set, or a pair of matrices in this set, we can always find the geodesic distance in this way. And here we use this symmetric polar decomposition, which is very similar to the sectorial decomposition. So it's like for every sectorial matrices, we can always find this so-called symmetric polar decomposition. And we got this geodesic distance. It's a metric between A and B. So with this metric, we can very easily to like reformulate or like formulate an alternative low phase rank approximation problem in this way. So here we just put the distance between A and E using this metric or the geodesic distance, and we restrict this phase rank of E to be no larger than R. So everything is the same except that we replace the objective function. So we don't use this E to divide A, but instead we measure their distance in terms of this geodesic distance, and we can get a very similar formulation. And luckily, this formulation gives rise to a very similar set of solutions in the Schmidt-Mirsky theorem flavor. So the set of solution is given by the R star truncation of the symmetric polar decomposition of this PA, UA, PA. And this UA is unitary. We just do a R truncation, like similarly in the singular value decomposition. Then we obtain the set of all the solutions to this low phase rank approximation in this formulation. So this is like, yeah. And in this way, we can say that this E, if we allow this E to have 4 phase rank, then E will just become A. And that's the best approximation. And if E is a low phase rank matrix, then this E will contain partial phase information of this matrix A. And if this E has 0 phase rank, it should be like the best positive definite approximation to the matrix A. So, okay, so this is how we solve this low phase rank approximation. And what we do if we see that the solution is not very desired, we just try to like improve or reformulate it slightly with this geodesic distance. So yeah, this comes to the end of this talk. So today I briefly like introduce this problem of low phase rank approximation, starting with the concept of phase and phase rank. And then we motivate ourselves by this low rank approximation. And then we develop this low phase rank approximation. And also, and again, motivated by the Schmidt-Mirsky theorem for the low rank approximation, we somehow obtain the counterpart results to this Schmidt-Mirsky theorem in the phase approximation. Yeah, and the future directions are actually quite clear because so far we didn't mention any concrete practical applications of the phase rank approximation. We know that the low rank approximation has many applications, like in the areas of systems and control, like model reductions, system identification, those subspace identification stuff. And it is also utilized in data compression, compressive sensing, and many communication problems. So low rank approximation is a very powerful and widely used scheme. So how about low phase rank approximation? Actually, we hope that they can be like utilized in a similar way as the low rank approximation, because we see that they share so many parallel stuff. We have so many parallel results between these two formulations, the rank and the phase rank. So we hope that in the end we can like apply these mathematical results to problems, those real world problems in systems and control, and try to have some nice application. And another direction to further extend this work is we formulate the general low phase rank approximation problem. We know that the general low rank approximation problem is not a convex problem, and we usually don't have those closed form solutions. So we have to take relaxations like convex relaxations and develop heuristic methods like nuclear norm heuristic, those log determinant heuristics. So many heuristic methods for low rank approximation. So maybe we can also like develop those heuristic methods for low phase rank approximation. And this is promising because there are many existing ways that we can mimic and we can learn from. Okay, so that's all. That's for today's talk. Thank you for listening. Any questions?
Thank you very much, Dee. So if there is any question. Ian, do you want to ask a question?
Hi, yeah. Thanks a lot, Dee. Very nice presentation, very clear. I have maybe two small questions, not really about the technical results that you presented,
okay.
But more about their kind of broader application or connection to other results. The first one is related to your remarks right at the end about the application. And we know, for example, in model reduction, balance truncation, and subspace identification and so on, we use singular value decomposition, low rank approximations, because what you end up with is a similar system with a much lower dimensional state space. And this simplifies many things that you want to do next, right? Analysis or control design. In this case, you're not actually changing the dimension of the system by, or the operator, I guess, by having a low rank approximation. So maybe could you expand a little bit on what kinds of tasks you think would get easier? Does it make some following analysis tasks easier to have a system or a matrix with low rank?
Very good question. Actually, this is actually what we are currently pursuing, because we really hope to find such nice applications. So so far we don't have a concrete plan, but we have some rough ideas. So maybe because this low phase rank, because if we are given a matrix, then we try to find a low phase rank approximation. Then the approximant tends to be close to positive definiteness, because so we know that the rank 0 matrix is positive definite. Then we may find some applications that desire this positive definiteness in this like discretized way. So it may allow some phase to be non-zero, but it hopes most of its phases to be 0. Okay. So we are trying to discover some applications in this way. We think about the model reduction, but we didn't quite find this result to be very useful, because we don't actually reduce the size of the problem in the sense of the rank. We don't remove those singular values, but we do remove the phase information of certain term. So, so far we only have those rough ideas. We don't have these concrete applications. Yeah.
Sure.
Thank you.
And a second question, you mentioned earlier on, I guess an application of these ideas is the small phase theorem, as you called it, related to small gain theorem. I mean, for linear and nonlinear systems, we have passivity theorems, which are in some way, you know, very obviously very closely related to positive real matrices, and also negative imaginary stability results. And they're in passivity for nonlinear systems, you can talk about kind of excess or deficit of passivity, and there are kind of loop transformations that allow you to still prove stability. Is this, I mean, is this what the small phase theorem is, or is it something else entirely? Or?
Okay, so so we know that the passivity index, some kind of using the passivity theorem and also with the index, we can formulate those small phase theorem as we know. But here, what I mean small phase theorem is slightly different from the existing ways, because we don't use this this index stuff. Instead we use this phase exceed or phase lack of. So we measure the difference between the matrix. I mean, we measure okay. So let me put it this way. So we are given a positive real system, and we can always make the system to be larger than it by introducing an additional phase shift. We don't introduce the index term. We don't put it. We don't put the graphic like left and right. We rotate it. We give it a phase shift. Then we use that phase exceed as our like phase index, for example, and we can do and by comparing the phase exceed or phase leakage of systems G and H in a closed loop, then we get the feedback stability. If the leakage and the exceed they just match, like the index, they have this index. Those indexes can be positive or negative. So the exceed can be positive and the leakage is negative. Then as long as we have this match, we get the stability. Yeah. So this is a rough idea.
Yeah. Okay. Thank you.
Thanks, Ian. Is there any other questions?
Iman, can I ask a question? It's Michael.
Sure.
Yeah. Thanks, Dee. I just have a question about the truncation step that you described. So just make sure that I understood what you said correctly. So you effectively throw away the ones with the largest phase, is that right?
Yes. Let me. Okay. Yeah. So for example here, so because this D term is a diagonal matrix.
Yep.
And we threw out. We don't throw it.
You throw it away. You replace it by one, right?
Yeah, we replace those larger one. The largest R terms by one. Yeah, this is all we do here.
Yeah.
And together with this half stuff, we take a square root.
Yeah. So is there any way of interpreting the impact of replacing that by one? So in terms of what, I guess I'm trying to understand the difference between what you start with and what you end up with when you replace all of those numbers by one, what that might mean.
And just before you answer Michael's question, I will ask a related question, which will be related to Ian's first question as well. Can you give an intuition about what happens to the spectrum of the operator when you do these replacements as well? Sorry.
Spectrum, you mean?
Sorry. Sorry, Michael, go ahead.
Yeah, what happens to, can you compare the spectrum of A to the spectrum of T times D with the largest ones replaced by one T star? How do they compare spectrally?
Okay, spectrum. So here the phase is, yeah. So let me see. Maybe we can understand this problem from the definition of phase. So a sectorial matrix is like this. So this numerical range contains all the spectrum of a matrix. So if lambda is a eigenvalue of this matrix C, then it is obviously contained in this numerical range on this complex plane. So if that is the case, and after like this low phase rank approximation, then actually we just put those non-zero phase to be zero. We put some of the large non-zero phase to zero. Then the spectrum will shrink.
Yeah. So are you narrowing the sector? Is that what happens effectively?
Yes.
You narrow
We're narrowing the sector, but I'm not sure if the truncate. I mean, if the truncation will just be a smaller, just be a subset of the original one, because the truncation seems, yeah, it should be. I think we just shrink the numerical range, and the truncation is just a subset of the original numerical range, and its spectrum should also shrink, like in a similar pattern.
Yeah, which makes sense that you're trying to make it look positive definite. You're trying to make it sit on the real axis. Yeah.
Yes, okay. Yes. Try to shrink the size and make it positive definite.
If you went all the way, I mean, interestingly, compared to SVD, I think it actually makes sense here to talk about a rank 0 approximation, whereas a rank 0 approximation is basically nothing, right? But rank 0, would that just be the projection onto the PSD cone? Of the matrix?
A rank 0 approximation is just we can view it like by this. I think it's good for us to. Sorry, it's slow. Yes. So if we take this symmetric polar decomposition, and we just remove this part, or we just take sectorial decomposition, it's also cool. So we just, the remaining stuff are the optimal rank 0 approximation. So also we can see from this thing. So this U contains all the phase information, and this is the gain information actually. So we take this geodesic distance, and if we use this 0 rank approximation, then the phase information is just nothing. The U part is identity. Then what we do is the gain match. We just match the gain, and here when we say gain, we just say actually it's just the positive definite part of this matrix.
Yeah, I guess if in the case of rank 0, when it becomes positive definite, or at least positive semi-definite, then in that case, you're projecting onto a convex cone of matrices that is a convex problem, and there are simple ways of doing that. For example, just take the well, I guess in this case your matrices are not necessarily symmetric, is that right? Or
you mean the rank 0 approximation?
Well, the original matrix is not necessarily symmetric.
Matrix is not symmetric.
The other thing as well here is that the geodesic distance probably is not the same as the Frobenius type distance that people use for projecting onto the positive semi-definite cone as well.
Yeah, that's what I was.
So it's a bit different.
So this geometry may be different from the Euclidean distance geometry. It could be like some Finsler geometry, those kind of stuff, but nevertheless we can formulate it like in different ways. Yeah.
So you'll get a different projection onto the.
Yes. We get the different geodesic distance. We get the different shortest line or shortest curve between 2 points.
Okay, thanks, D again. That was a good discussion there as well. Any other questions? If not, let's thank Dee again for the very interesting talk that he gave this afternoon, and see everyone next week. Also, before
Okay, see you.
everyone runs away, I